Let us look at definite integrals using reduction formula. So we have integral of sine to the power of nx dx from 0 to pi by 2. So remember the definite integral formula using reduction method. We have minus 1 by n sine to the power of n minus 1 x times cos x from 0 to pi by 2 plus n minus 1 by n times the integral of sine to the power of n minus 2 x dx from 0 to pi by 2. Now here what happens? What is cos pi by 2? It is 0. What is sine 0? It is 0. So the first term disappears. So we are left with only the second term. Now here again we have a integral to the power of n minus 2. So this can be written as n minus 1 by n times I sub n minus 2. So applying the formula again for I sub n minus 2, we get I sub n minus 2 is equal to n minus 2 minus 1 by n minus 2 times I sub n minus 2 minus 2. Okay, simplifying this, we get I sub n minus 2 is equal to n minus 3 by n minus 2 times I sub n minus 4. Applying it again, we get I sub n minus 4 is equal to n minus 4 minus 1 by n minus 4 times I sub n minus 4 minus 2. Now simplifying this, we get I sub n minus 4 is equal to n minus 5 by n minus 4 times I sub n minus 6. If we go through these, we can see a pattern build up. So the pattern is I sub n is equal to n minus 1 by n times this is I sub n minus 2, which is n minus 3 by n minus 2 times I sub n minus 4. I sub n minus 4 is n minus 5 by n minus 4. And it will keep on going till some factor k. Now here k would be what? As we have seen previously, if n is odd, that means sine to the power of n minus 2 would be 1 at some point, which is sine x. And the integral of that sine x is minus cos x. Minus cos pi by 2 is 0 and minus cos 0 is 1. So minus minus 1. So 1. Similarly, k will be equal to pi by 2 if n is even. Because if n is even, at some point it will become 0. So we will end up with sine to the power of 0x, which is nothing but 1. So integral of dx, it will be x. So pi by 2 minus 0, which is pi by 2. Now let's actually solve some problems. In the first problem, let's look at n equal to 0. So we have integral from 0 to pi by 2 of sine 0 x dx. Now this is so straightforward that we could use it without using this method itself. Sine 0 of x is 1 and integral of 1 dx is x from 0 to pi by 2, which means I sub naught is equal to pi by 2. But if we had to apply this pattern or this method, then what would we have? The n minus 1 by n itself would not be applicable. Yes. So why? Because 0 minus 1 by n. So we end up with a negative number. So which means we directly go to k. And for k, we have a conditional value. If n is odd, it is 1. If n is even, it is pi by 2. And 0 is considered to be even. So I naught equal to pi by 2. Similarly, if we take n equal to 1, we have integral from 0 to pi by 2 of sine x dx. Without using this method, we can solve this. So sine x integral is minus cos x from 0 to pi by 2 minus cos pi by 2 minus cos 0, which means I sub 1 is equal to 1. Now, but if we have to apply this pattern, then what happens? Or this method? Then again, you will notice that n is 1, so 1 minus 1, 0. So again, this term will not be applicable, and any of the other factors. So we directly go to k. And since 1 is odd, it is k is 1. So either way, we get the same values. Now let's look at the third one. Let's take a odd power of sin x. So integral from 0 to pi by 2 of sine to the power of 5x dx. What do we get? See, we don't have to bother with all these things. We have already achieved a pattern. So n minus 1, that is 5 minus 1 by 5 times 5 minus 3 by 5 minus 2. And we don't need to go further because 5 minus 5 becomes 0. So which means we have 4 by 5 times 2 by 3, which is equal to 8 by 15. Okay, now let's look at the fourth one. I is equal to integral from 0 to pi of x times sine to the power of 8x dx. Now here we have x as well along with the sine power. Let's see how this works out. Now one of the integral properties we can apply here. So integral from 0 to pi x sine to the power of 8x can be written as integral from 0 to pi of pi minus x times sine to the power of 8 of pi minus x dx. They both are the same. So here sine pi minus x will be what? It will be sine x itself. So we have integral from 0 to pi of pi minus x times sine to the power of 8x dx. Now let's distribute this and split the integrals. We have integral from 0 to pi of pi times sine to the power of 8x dx minus integral from 0 to pi of x times sine to the power of 8x dx. And this is nothing but I itself. So taking it to the other side, it becomes 2I is equal to pi is a constant, we take it out. So pi times the integral 0 to pi of sine 8x dx. Okay, so basically what have we achieved? We have got rid of x and in its place we have a constant pi. 2I is equal to, now the right hand side what we are doing is we are taking or changing the limits to 0 to pi by 2 and we are doubling the integral. So we have 2 pi times 0 to pi by 2 of sine 8x dx. 2 cancel out. We have I is equal to pi times the integral 0 to pi by 2 of sine 8x dx. This pretty straightforward now. I is equal to pi times 8 minus 1 by 8, 8 minus 3 by 8 minus 2, times 8 minus 5 by 8 minus 4, times 8 minus 7 by 8 minus 6. And we can stop at this point as far as this pattern is concerned. Why? Because what will happen next in the denominator is 8 minus 8. So in the denominator, we'll end up with 0. So we stop at this point. Times, and since 8 is even, so the last term would be, or last factor would be pi by 2. Simplifying this, we get I is equal to 7 by 8 times 5 by 6 times 3 by 4 times 1 by 2. times pi times pi square by 2. And simplifying it further, we get I is equal to 35 pi square by 256. Neat, right? That was interesting. Okay. If you found this useful, don't forget to like, share, and subscribe. Questions and suggestions are always welcome. Thanks for watching. See you in the next session. That's it. Bye.